Imagine the fastest thing you can think of: a cheetah sprinting across the savannah, a rocket blasting off into space. Now imagine something moving much, much faster. That something is light, the ultimate speedster of the cosmos. It travels at a mind-boggling 299,792,458 meters per second, a speed so fast that it could circle the Earth over 7 times in just 1 second. This incredible speed isn't just a fun fact, it's a fundamental law of the universe, a cosmic speed limit that nothing can break. But why is the speed of light so important? It all comes down to Albert Einstein's groundbreaking theory of relativity. This theory hinges on the idea that the speed of light in a vacuum is constant, a universal constant that underpins our understanding of how the universe works. The constancy of the speed of light has profound implications for our understanding of the cosmos. It tells us that space and time are not absolute, but are intertwined in a way that we never imagined before Einstein. To understand this, imagine 2 people observing a beam of light. One person is standing still, while the other is on a spaceship moving at a significant fraction of the speed of light. Common sense would suggest that the person on the spaceship would perceive the light to be traveling slower, right? However, Einstein's theory of relativity tells us otherwise. Both observers, regardless of their relative motion, would measure the speed of light to be exactly the same. This mind-bending concept has been experimentally verified countless times, proving that our everyday intuition about speed doesn't hold true at the cosmic level. This phenomenon, known as time dilation and length contraction, ensures that the speed of light remains constant for all observers. The quest to measure the speed of light has captivated scientists for centuries. Early attempts, though ingenious, provided only rough estimates. One of the first to attempt this feat was Danish astronomer Ole Romer in the 17th century. By carefully observing the eclipses of Jupiter's moon Io, Romer noticed that the eclipses appeared to occur later when Earth was farther from Jupiter in its orbit. He deduced that this discrepancy was due to the finite speed of light, as it took longer for light to travel the greater distance. Romer's work provided the first quantitative measurement of the speed of light, a remarkable achievement for his time. In the 19th century, physicists James Clerk Maxwell and Albert Michelson made significant contributions to our understanding of light. Maxwell's equations unified electricity, magnetism, and light, demonstrating that light itself is an electromagnetic wave. The Michelson-Morley experiment, designed to detect a hypothetical medium called luminiferous ether, unexpectedly failed to detect any variation in the speed of light, paving the way for Einstein's theory of relativity. The Michelson-Morley experiment, despite its seemingly negative result, was nothing short of a silent earthquake in the world of physics. It shattered the prevailing notion of a luminiferous ether, a hypothetical medium that was thought to permeate all of space and provide a reference frame for light waves to travel. The idea of an ether was so deeply ingrained in the scientific thought of the time that the experiment's null result was met with disbelief and confusion. Many attempts were made to explain away the results, but none could stand up to scrutiny. If there was no ether, then what was the speed of light relative to? Einstein's theory of relativity provided the answer. The speed of light is relative to nothing at all. It is a universal constant, independent of the motion of the observer or the source of light. This radical concept challenged our most fundamental understanding of space and time, forcing physicists to rethink the very nature of the universe. The Michelson-Morley experiment became a cornerstone of modern physics, paving the way for a deeper understanding of the cosmos. The constancy of the speed of light isn't just a theoretical concept. It's supported by observations from the farthest reaches of the observable universe. One of the most compelling pieces of evidence comes from the cosmic microwave background radiation, the faint afterglow of the Big Bang. This radiation, discovered in 1964, provides a snapshot of the universe as it was just 380,000 years after the Big Bang. The CMB is remarkably uniform in temperature in all directions, with only tiny fluctuations of a few parts per 100,000. These fluctuations contain a wealth of information about the early universe, including the speed of light at that time. By analyzing the pattern of these fluctuations, cosmologists can infer that the speed of light has remained remarkably constant over billions of years. This consistency provides strong evidence for the constancy of the speed of light and supports the fundamental principles of modern cosmology. The CMB serves as a powerful reminder of the vastness and wonder of the universe we inhabit. While the constancy of the speed of light is a cornerstone of modern physics, some theories propose that it might not have always been this way. These theories, known as variable speed of light theories, suggest that the speed of light might have been different in the early universe. This radical concept could potentially solve some of the most perplexing mysteries in cosmology. One such mystery is the horizon problem, which arises from the incredible uniformity of the cosmic microwave background radiation. The problem lies in the fact that regions of the early universe separated by vast distances appear to have been in thermal equilibrium. However, these regions are so far apart that they wouldn't have had enough time since the Big Bang to exchange information or energy even at the speed of light. VSL theories offer a potential solution to this puzzle. If the speed of light were much faster in the early universe than light, and thus information, could have traveled much greater distances in the same amount of time. This would have allowed distant regions of the early universe to communicate and reach thermal equilibrium, explaining the observed uniformity of the CMB. While VSL theories offer intriguing solutions to cosmological puzzles like the horizon problem, they also face significant challenges. One of the biggest hurdles is that a changing speed of light would have profound implications for our understanding of fundamental physics. For example, the speed of light is intimately linked to the electromagnetic force, one of the 4 fundamental forces of nature. If the speed of light were to change, it would imply a change in the strength of the electromagnetic force, potentially disrupting the delicate balance that governs the interactions of particles and the formation of atoms. Furthermore, VSL theories would require significant modifications to Einstein's theory of relativity, which is based on the premise of a constant speed of light. Despite these challenges, VSL theories remain an active area of research in theoretical physics. While there's currently no conclusive evidence to support a changing speed of light, the possibility continues to intrigue scientists as they search for a more complete understanding of the universe and its fundamental laws. The quest to understand the speed of light, its constancy, and its potential for variation is a testament to the insatiable curiosity of the human spirit. From the early attempts to measure its value to the development of groundbreaking theories that revolutionized our understanding of the universe, the speed of light has played a central role in shaping our view of the cosmos. While the evidence overwhelmingly supports the constancy of the speed of light as we know it today, the possibility of a variable speed in the early universe continues to tantalize physicists and cosmologists alike. The search for answers takes us to the very edge of human knowledge, where established theories meet the unknown. It's a journey driven by a thirst for understanding, a desire to unravel the deepest mysteries of the universe. Whether the speed of light is ultimately found to be truly constant or subject to variation, the pursuit of this knowledge will undoubtedly lead to new discoveries, challenging our assumptions and expanding our horizons. As we continue to explore the vast expanse of space and time, the speed of light will undoubtedly serve as our guide, illuminating the path towards a deeper understanding of the universe and our place within it.